On July 13, 1959, at 20:45 Pacific Standard Time, the sodium reactor experiment at Santa Susana Field Laboratory experienced a nuclear incident that would remain classified for decades. The reactor, an experimental liquid metal-cooled design operating 18 miles northwest of Hollywood, had been generating electrical power for Southern California Edison since 1957. Operating parameters that evening showed normal primary coolant flow at 1,250 gallons per minute, reactor power at 6.5 megawatts thermal, and primary sodium temperature at 945 degrees Fahrenheit. The facility operated without a containment dome, based on the engineering assumption that liquid metal reactors were inherently safer than water-cooled designs. This assumption would prove catastrophically incomplete. The sequence that followed was not a sudden catastrophic failure, but a systematic breakdown in which monitoring instruments provided data that was technically accurate, yet diagnostically misleading. Operators followed established procedures, regulatory oversight functioned as designed, and safety systems responded according to their engineering specifications. The reactor core sustained damage that released radioactive materials directly into the Southern California atmosphere, yet no public notification occurred. The incident was classified, investigated internally, and managed through information control rather than physical containment. This failure resulted from a fundamental mismatch between experimental reactor design assumptions and operational reality. The facility operated under commercial power generation protocols while conducting experimental nuclear research in an uncontained environment near populated areas. The institutional framework treated experimental uncertainty as manageable risk while public proximity was considered irrelevant to operational safety. Information classification substituted for engineering barriers, creating a system where technical success and public protection became structurally incompatible. The Santa Susana Field Laboratory represented a convergence of military nuclear research priorities with civilian power development objectives. Established in 1947 on 2,668 acres in the Simi Hills, the facility was deliberately located in what was then considered remote terrain, sufficiently isolated to conduct dangerous experimental work away from populated centers. The Atomics International Division of North American Aviation selected the site specifically for nuclear reactor development, anticipating that liquid metal cooling technology would revolutionize both military and civilian nuclear applications. The sodium reactor experiment embodied this convergence, designed simultaneously as a proof of concept for advanced reactor physics and as a functioning power plant delivering electricity to the regional grid. The fundamental design philosophy underlying the sodium reactor experiment emerged from theoretical advantages that liquid sodium offered over conventional water cooling. Sodium's superior heat transfer properties allowed higher operating temperatures and thermal efficiency, while its chemical stability at reactor operating conditions eliminated the high-pressure vessels required for water-cooled systems. Most significantly, sodium's neutron absorption characteristics were minimal compared to water, permitting more efficient fuel utilization and reactor physics. These theoretical advantages led designers to conclude that sodium-cooled reactors required fewer engineered safety systems than water-cooled designs, since the coolant itself provided inherent stability under most credible accident scenarios. This design confidence translated directly into the decision to operate without containment structures. Engineering calculations demonstrated that sodium coolant would not flash to steam under loss of cooling scenarios, eliminating the pressure surge mechanisms that necessitated massive containment domes for water-cooled reactors. The liquid metal's high boiling point meant that coolant loss scenarios would develop slowly, providing operators with extended time to implement corrective actions before core damage could occur. Furthermore, sodium's chemical compatibility with reactor materials reduced corrosion concerns that might compromise primary system integrity over extended operations. However, these design advantages were calculated under steady-state operational assumptions that did not account for dynamic failure mechanisms specific to liquid metal systems. The theoretical models assumed that sodium would remain in liquid phase throughout all credible accident scenarios, maintaining its superior heat transfer properties and chemical stability. These calculations did not adequately address conditions where fuel element failures might introduce gas bubbles into the sodium coolant, dramatically altering flow dynamics and heat transfer effectiveness. The design basis also failed to consider how fission gases released from damaged fuel elements would behave in liquid sodium, particularly regarding their eventual release pathways to the atmosphere. The instrumentation systems for the sodium reactor experiment reflected these design assumptions by prioritizing operational efficiency over comprehensive safety monitoring. Temperature sensors were positioned to measure bulk sodium coolant conditions rather than localized hotspots that might indicate fuel element distress. Flow measurement systems tracked total sodium circulation through the primary loop, but provided limited information about flow distribution within individual fuel channels. Power-level instrumentation monitored neutron flux in reactor core regions optimized for normal operations, with reduced sensitivity in zones where damaged fuel elements might create abnormal neutron absorption patterns. This instrumentation philosophy proved adequate for normal operations, but created significant diagnostic blind spots during abnormal conditions. The temperature monitoring system could detect overall coolant heating, but might not identify localized boiling or gas bubble formation that would compromise heat removal from specific fuel elements. Flow instrumentation would continue indicating normal circulation even if gas bubbles were reducing heat transfer effectiveness in portions of the reactor core. Power level measurements would show successful control rod insertion and power reduction while remaining insensitive to ongoing fission product release from previously damaged fuel. The regulatory framework governing experimental reactor operations in 1959 reflected the institutional assumption that military-derived nuclear technology could be safely adapted for civilian applications through existing oversight mechanisms. The Atomic Energy Commission treated the Santa Susana facility as both a military research installation and a civilian power plant, applying regulatory standards that were appropriate for neither category. Military nuclear facilities operated under security classifications that prioritized information control over public safety transparency, while civilian power plants were regulated under industrial safety standards designed for conventional steam generating stations. The sodium reactor experiment fell into a regulatory gap where military classification protocols prevented public oversight while civilian safety standards were inadequate for experimental reactor risks. This regulatory ambiguity was compounded by the geographical evolution of Southern California during the reactor's operational lifetime. When the facility was established in 1947, the surrounding Simi Hills region was genuinely remote, with residential development limited to established communities several miles away. However, California's post-war population growth steadily expanded suburban development toward the laboratory boundaries. By 1959, residential neighborhoods existed within miles of the reactor site, yet regulatory oversight had not evolved to address the changing risk profile created by increasing population density near experimental nuclear facilities. The institutional culture at Santa Susana reflected military nuclear program priorities that emphasized technical achievement and schedule adherence over public safety considerations that might compromise mission objectives. Engineers and operators were trained to view reactor operations as technical challenges, requiring innovative solutions rather than as public safety responsibilities, demanding conservative approaches. This cultural framework encouraged pushing operational boundaries to gather experimental data while treating safety margins as engineering parameters to be optimized rather than absolute constraints. Personnel training programs reflected this institutional bias by emphasizing reactor physics, thermal hydraulics, and system optimization, while providing minimal preparation for abnormal conditions that might require shutting down the reactor and terminating experimental programs. Operators learned to maximize power output, maintain stable operations during transients, and extract useful experimental data from reactor behavior. Training for accident scenarios focused on maintaining system control rather than recognizing when continued operations might pose unacceptable risks to public safety. The organizational structure at Santa Susana created functional separation between research objectives and operational safety that reflected military nuclear program management approaches. Research engineers established experimental goals and operating parameters based on technical objectives, while operations staff implemented these directives according to established procedures. Safety analysis remained largely theoretical, conducted by specialists who were not directly involved in day-to-day operations and whose recommendations could be overruled by program management priorities. This organizational separation meant that operations staff had limited authority to modify experimental programs based on safety concerns, while research staff had limited operational experience to understand how their experimental objectives might interact with actual reactor behavior under abnormal conditions. The resulting decision-making process prioritized technical data collection over operational conservatism, creating institutional pressure to continue experimental programs even when reactor behavior deviated from predicted patterns. The information classification system governing reactor operations created additional institutional barriers between operational reality and public safety considerations. Technical data regarding reactor performance, operational problems, and safety concerns were routinely classified to protect military nuclear program objectives, preventing external oversight that might have identified public safety risks. This classification system functioned effectively to maintain program security, but eliminated independent safety review that might have recognized the inadequacy of uncontained reactor operations near populated areas. The combination of these design, regulatory, and institutional factors created a system where experimental reactor operations proceeded under assumptions that became progressively less valid as technical understanding evolved and demographic conditions changed. The liquid metal cooling technology offered genuine advantages under normal operational conditions, but these advantages came with failure modes that were poorly understood and inadequately monitored. The regulatory framework provided oversight that was appropriate for neither military research nor civilian power generation, while institutional priorities emphasized technical achievement over public protection. When the reactor experienced core damage on July 13, 1959, these foundational assumptions were systematically tested against physical reality. The theoretical advantages of liquid sodium cooling became liabilities when fuel element failures introduced conditions beyond the design basis. The instrumentation systems designed for operational efficiency proved inadequate for diagnosing abnormal conditions. The regulatory framework lacked mechanisms for rapid response to public safety threats, while institutional classification protocols prevented timely recognition of the incident's significance. The failure was not the result of individual errors or component malfunctions, but rather the inevitable consequence of operating an experimental reactor system under assumptions that could not accommodate the full spectrum of possible failure mechanisms. The design philosophy, regulatory oversight, and institutional management all functioned according to their intended purposes, yet collectively created conditions where core damage could occur and radioactive releases could continue without triggering appropriate emergency responses. The operational culture at Santa Susana Field Laboratory had evolved through a decade of experimental reactor programs that normalized technical risk-taking while maintaining the appearance of rigorous safety protocols. By 1959, operators and engineers had accumulated extensive experience with sodium-cooled reactor systems, creating institutional confidence that liquid metal technology was fundamentally well understood and controllable. This confidence was built on successful resolution of numerous minor operational problems that had been systematically categorized as normal variations rather than potential indicators of deeper system vulnerabilities. The training programs for sodium reactor experiment operators reflected military nuclear program approaches that emphasized technical competence and operational flexibility over procedural compliance. Personnel were trained to understand reactor physics principles, thermal hydraulic behavior, and system responses sufficiently to make real-time adjustments based on changing conditions. This approach produced highly skilled operators who could maintain reactor operations during transients and equipment malfunctions that might have forced shutdowns under more conservative operating philosophies. However, the same training philosophy created cognitive biases toward maintaining operations rather than recognizing when abnormal conditions indicated fundamental threats to system integrity. Operator training scenarios focused primarily on equipment failures and operational transients that could be managed through skillful manipulation of control systems. Training exercises simulated pump failures, control rod malfunctions, power level transients, and various combinations of equipment problems that required operators to demonstrate their ability to maintain reactor control under challenging conditions. These training programs were highly effective at developing operational competence for managing reactor systems during normal and moderately abnormal conditions. However, they provided limited preparation for recognizing conditions where continued operation might be inappropriate regardless of the operator's technical ability to maintain system control. The control room design for the sodium reactor experiment reflected 1950s industrial control philosophy that prioritized operational efficiency over comprehensive system monitoring. Control panels were organized around operational functions rather than safety parameters, with instruments grouped according to their relevance for power production, rather than their significance for detecting abnormal conditions. Primary displays showed reactor power level, coolant flow rates, temperatures, and control rod positions prominently, while instruments that might indicate fuel element condition or fission product release were located in secondary positions or absent entirely. This control room layout reinforced operational priorities by making production-related parameters immediately visible while requiring deliberate effort to access information about reactor conditions that might indicate developing problems. Operators developed working patterns focused on maintaining stable power output, optimizing thermal efficiency, and responding to control system demands. The instrument layout encouraged attention to parameters that could be directly controlled while providing limited feedback about reactor conditions that might require shutdown decisions rather than control adjustments. The shift scheduling and staffing patterns at Susana reflected experimental program priorities that required continuous reactor operations to maximize data collection opportunities. Operators worked extended shifts during experimental campaigns, maintaining reactor operations for weeks or months with minimal interruptions. This scheduling approach produced operational teams with intimate knowledge of specific reactor behavior patterns and extensive experience managing minor system variations. However, continuous operations also created normalization pressures where operators became accustomed to accepting small deviations from nominal conditions rather than investigating their underlying causes. Maintenance practices for sodium systems had evolved to accommodate the unique properties of liquid metal cooling while maintaining operational availability for experimental programs. Sodium's reactivity with air and water required specialized procedures for any maintenance work involving primary system components. Small sodium leaks were considered routine maintenance issues that could be managed through system modifications and cleanup procedures rather than operational shutdowns. Operators became skilled at identifying sodium leak signatures and implementing workarounds that minimized experimental program disruptions. These maintenance practices created institutional tolerance for primary system integrity problems that would have been unacceptable in other reactor designs. Small leaks were treated as manageable nuisances rather than potential indicators of more serious system degradation. Operators developed confidence in their ability to manage sodium system problems through technical solutions that maintained experimental program schedules. This operational philosophy worked effectively for minor system problems, but created cognitive frameworks that discouraged conservative responses to more significant system changes. The organizational communication patterns between research staff and operations personnel reflected military nuclear program hierarchies that emphasized technical authority over operational experience. Research engineers established experimental objectives and operating parameters based on theoretical calculations and program requirements, communicating these directives to operations staff through formal procedures and technical specifications. Operations personnel were expected to implement research directives while providing feedback about system performance and operational constraints. However, this communication structure created information barriers between theoretical knowledge and practical experience that limited organizational learning from operational problems. Research staff had limited direct exposure to actual reactor behavior under abnormal conditions, while operations staff had limited authority to modify experimental programs based on their operational observations. The resulting organizational dynamic discouraged critical evaluation of research assumptions based on operational experience, maintaining theoretical frameworks that might not accurately reflect actual system behavior. The documentation and reporting systems for reactor operations emphasize technical achievement and experimental data collection over safety-related observations that might indicate developing problems. Operational logs focused on power levels, experimental parameters, and system performance metrics that demonstrated successful completion of research objectives. Unusual observations or minor equipment problems were typically documented as maintenance issues or operational notes, rather than potential safety concerns requiring investigation. This documentation approach meant that patterns of minor problems that might indicate fundamental system changes were not systematically analyzed or communicated to research staff who might recognize their broader significance. Individual operators might notice trends in system behavior, but the reporting structure did not facilitate comprehensive analysis of whether these trends indicated normal operational variations or developing safety concerns. The regulatory oversight structure for the sodium reactor experiment reflected Atomic Energy Commission priorities that emphasized technical progress and security considerations over systematic safety evaluation. Regulatory inspections focused on compliance with technical specifications and security procedures, rather than comprehensive assessment of operational safety practices. Inspectors were typically nuclear engineers with theoretical knowledge but limited practical experience with liquid metal reactor operations, limiting their ability to recognize operational practices that might indicate developing safety problems. The AEC's regulatory approach also reflected institutional assumptions that experimental reactor programs were inherently safer than full-scale commercial operations due to their smaller size and limited power levels. This assumption led to regulatory frameworks that provided less intensive oversight for experimental facilities, despite their operation of unproven technologies under less conservative design standards. The resulting regulatory environment encouraged experimental programs to proceed with minimal external oversight, while providing limited independent assessment of whether operational practices adequately addressed the unique risks associated with experimental reactor technologies. The emergency response planning for the Santa Susana site reflected military nuclear program approaches that prioritized facility security and information control over public safety considerations. Emergency procedures focused on protecting personnel within the facility and maintaining security of classified information rather than assessing or mitigating potential off-site consequences of reactor accidents. Emergency response teams were trained to handle facility emergencies that might affect on-site personnel but had limited preparation for evaluating or responding to potential public safety threats. This emergency planning approach meant that operational staff had clear procedures for responding to equipment failures and facility emergencies, but lacked frameworks for recognizing when reactor conditions might pose risks to off-site populations. Emergency response protocols emphasized containing problems within facility boundaries and maintaining communication security, rather than evaluating whether developing situations might require public notification or protective actions. The quality assurance systems for reactor operations reflected experimental program priorities that emphasized technical innovation over systematic error prevention. Quality control focused on ensuring that experimental objectives were achieved and that technical specifications were met, rather than systematically identifying and correcting operational practices that might contribute to safety problems. Review processes emphasize technical achievement and schedule adherence while providing limited systematic evaluation of whether operational practices were appropriate for the unique risks associated with uncontained reactor operations near populated areas. These quality assurance approaches worked effectively for achieving experimental program objectives, but created organizational blind spots regarding the adequacy of operational practices for protecting public safety. Technical success in achieving experimental goals became the primary metric for evaluating operational performance, while systematic assessment of safety practices received secondary consideration. This quality assurance philosophy reinforced organizational priorities that valued technical achievement over conservative operational practices. The combination of these organizational, training, and cultural factors created operational conditions where highly competent technical personnel operated an experimental reactor under frameworks that systematically discouraged recognition of conditions that might require conservative responses for public safety protection. Operators were trained and equipped to maintain reactor control under challenging conditions, but were not prepared to recognize when their technical ability to maintain control might be insufficient to ensure public safety. The organizational structure valued technical achievement and experimental data collection over operational conservatism, creating institutional pressure to continue operations even when system behavior deviated from normal patterns. When abnormal conditions began developing in the sodium reactor experiment on July 13, 1959, these organizational and cultural factors would interact with technical system limitations to create decision-making frameworks that prioritized maintaining experimental operations over investigating whether developing problems might indicate fundamental threats to public safety. The operators and engineers responsible for the reactor were highly skilled professionals operating according to established procedures and organizational priorities, yet these same factors would contribute to systematic underestimation of the significance of developing abnormal conditions. The power excursion that began at approximately 20:45 PST on July 13, 1959, appeared initially as a routine operational transient of the type that sodium reactor experiment operators had successfully managed hundreds of times during the reactor's operational history. Reactor power increased from its steady-state level of 6.5 megawatts thermal to approximately 7.8 megawatts over a period of several minutes, triggering automatic control rod insertion that brought power back toward normal levels. Primary sodium flow continued at 1,250 gallons per minute. Bulk coolant temperatures remained within normal operating ranges, and control rod positions indicated successful power reduction. From the operator's perspective in the control room, the transient appeared to be a minor power level fluctuation that had been successfully controlled through normal automatic protective systems. However, this apparent return to normal conditions masked fundamental changes in reactor core conditions that the instrumentation system was not designed to detect or communicate to operators. The power excursion had created thermal stress conditions in fuel elements that exceeded design specifications, initiating cladding failures that would release fission products directly into the primary sodium coolant. These failures occurred in fuel elements located in high-power regions of the reactor core, where localized heating had exceeded the thermal limits of the uranium-molybdenum alloy fuel and its magnesium cladding system. The fuel element design for the sodium reactor experiment reflected 1950s materials technology that was adequate for normal operating conditions but had limited margins for thermal transients. The uranium-molybdenum fuel alloy provided good neutron economy and thermal conductivity under steady-state conditions, while the magnesium cladding offered low neutron absorption and adequate corrosion resistance in sodium coolant. However, the thermal expansion characteristics of these materials created stress concentrations during rapid power changes that could compromise cladding integrity even when bulk fuel temperatures remained within nominal limits. During the power excursion, differential thermal expansion between the fuel alloy and magnesium cladding created mechanical stresses that exceeded the cladding's yield strength in regions where fuel element geometry or neutron flux. Distribution concentrated thermal loads. The cladding failures that resulted were not catastrophic ruptures but rather small cracks that allowed fission gases to escape from fuel elements while maintaining overall structural integrity. These failures were precisely the type of degradation that the reactor's instrumentation system was least capable of detecting, since they did not significantly affect bulk coolant properties or overall heat removal capability. The fission gases released through these cladding failures dissolved in the liquid sodium coolant, where they remained largely invisible to the temperature and flow instrumentation that operators relied upon for assessing reactor condition. Sodium's excellent heat transfer properties meant that the additional heat load from fission gas energy release was effectively distributed throughout the coolant system, preventing localized temperature increases that might have indicated fuel element problems. The primary sodium circulation system transported these dissolved gases throughout the reactor cooling loop, where they gradually separated from the liquid sodium and accumulated in gas spaces within the primary system. This gas accumulation process created conditions that fundamentally altered reactor physics and heat transfer characteristics, while remaining largely invisible to control room instrumentation. As fission gases separated from the sodium coolant, they formed bubbles within fuel channels that reduced effective heat transfer area and modified coolant flow patterns. The reduced heat transfer effectiveness created positive feedback conditions where decreased cooling led to higher fuel temperatures, additional cladding stress, and potentially more extensive fuel element failures. The temperature monitoring system for the sodium reactor experiment was designed to measure bulk coolant conditions at the inlet and outlet of major system components, rather than detecting localized changes within individual fuel channels. This instrumentation philosophy was appropriate for normal operations, where temperature variations were gradual and distributed throughout the coolant system. However, it proved inadequate for detecting the localized cooling degradation that resulted from gas bubble formation in specific fuel channels, since these local effects were averaged out in the bulk temperature measurements that operators monitored. Similarly, the flow measurement systems tracked total sodium circulation through major system components, but provided no information about flow distribution within individual fuel channels or the presence of gas bubbles that might be reducing heat transfer effectiveness in portions of the reactor core. Operators continued to observe normal flow rates through primary system instruments, while actual heat removal capability was being compromised by gas accumulation in regions of the core that remained invisible to their monitoring systems. The neutron flux instrumentation that monitored reactor power levels and control rod effectiveness also failed to provide clear indication of the developing fuel element problems. The fission gas release from damaged fuel elements represented a small fraction of total reactor fission product inventory, insufficient to create detectable changes in overall neutron flux patterns. Control rod insertion successfully reduced reactor power to desired levels, demonstrating that reactor criticality remained under control even while fuel integrity was being compromised in ways that did not affect overall neutron balance. These instrumentation limitations created a systematic divergence between the reactor conditions that operators observed through their control room displays and the actual physical situation developing within the reactor core. The instruments accurately reported the parameters they were designed to measure, but these parameters no longer provided valid representations of reactor safety status under the abnormal conditions that were developing. Operators observed successful power control, normal flow rates, and acceptable temperatures while the reactor was experiencing progressive fuel failures and accumulating gas bubbles that degraded heat removal capability. The automatic safety systems for the sodium reactor experiment functioned exactly as designed during this sequence, inserting control rods in response to power level increases and maintaining reactor operation within technical specification limits. These systems were designed to prevent reactor damage from power excursions and loss of flow events that represented the most credible accident scenarios for liquid metal reactors. However, they were not designed to detect or respond to fuel element integrity problems that occurred within these operational limits, particularly when such problems developed gradually and remained below the threshold for activating automatic protection systems. The emergency operating procedures that operators followed during this sequence were appropriate for managing power transients and control system malfunctions, but provided no guidance for recognizing or responding to fuel integrity problems that might occur without clear instrumentation indication. These procedures assumed that instrumentation systems would provide reliable indication of any reactor conditions requiring emergency response, an assumption that proved invalid when fuel failures created conditions that remained invisible to control room displays. Operations personnel faced a fundamental diagnostic problem that their training and procedures had not prepared them to recognize. The reactor was simultaneously under control, according to all available instrumentation, while experiencing core damage that posed potential risks to public safety. The control systems were responding appropriately, power levels were stable, coolant circulation was normal, and temperatures were acceptable. Yet fuel elements were failing. Fission products were being released into the coolant system, and gas accumulation was creating conditions for additional fuel failures. This diagnostic ambiguity was compounded by the reactor's operational history, which included numerous minor transients and equipment problems that had been successfully managed without shutting down the reactor. Operators had accumulated extensive experience with power level variations, control system irregularities, and cooling system problems that appeared more severe than the current situation. Their operational experience suggested that the current conditions represented a minor problem that could be managed through continued, normal operations, rather than a fundamental threat requiring reactor shutdown. The shift supervisor's decision to continue normal operations reflected reasonable engineering judgment based on available information and established operational practices. All monitored parameters indicated successful transient management, automatic safety systems had functioned as designed, and reactor conditions appeared stable. Shutting down the reactor would terminate ongoing experimental programs and require extensive investigation to determine the cause of the power excursion, potentially affecting facility mission objectives without clear safety justification. However, this decision to continue operations was based on information systems that had become fundamentally unreliable under the conditions that were developing, even though this unreliability was not apparent to operations personnel. The instrumentation continued to function correctly in terms of measuring the physical parameters it was designed to monitor, but these parameters no longer provided valid indication of reactor safety status. The divergence between instrument indication and actual reactor conditions would continue to widen as damaged fuel elements released more fission products, and gas accumulation further degraded cooling effectiveness. By midnight on July 13th, approximately 3 hours after the initial power excursion, reactor operations appeared to have returned completely to normal from the operator's perspective. Power levels were stable, control systems were responding appropriately, and all monitored parameters were within acceptable ranges. The decision to continue normal operations appeared vindicated by stable reactor conditions that demonstrated successful management of what had initially appeared to be a minor operational problem. Yet during this same period, the physical reality within the reactor core was evolving in ways that would eventually make the situation unrecoverable. Additional fuel elements were experiencing cladding failures as gas accumulation reduced cooling effectiveness in affected channels. Fission product release rates were increasing as more fuel elements lost integrity, while gas bubble formation was creating flow instabilities that further compromised heat removal. The reactor was entering a progressive degradation sequence where each fuel failure made additional failures more likely, creating positive feedback conditions that would eventually exceed the capability of automatic protection systems to maintain safe operation. The progressive fuel element degradation that accelerated throughout the early morning hours of July 14, 1959, followed predictable thermodynamic and materials science principles that were well understood individually, but had never been systematically analyzed in combination under actual reactor operating conditions. The uranium-molybdenum fuel alloy's response to thermal cycling created microstructural changes that increased susceptibility to cladding failure, while the magnesium cladding's corrosion behavior in sodium coolant containing dissolved fission products accelerated degradation processes that normally occurred over months or years of operation. The initial cladding failures had released primarily gaseous fission products, xenon, krypton, and iodine isotopes that dissolved readily in liquid sodium at reactor operating temperatures. This dissolution process temporarily masked the extent of fuel damage by preventing immediate gas bubble formation that might have created detectable flow or temperature anomalies. However, as fission gas concentrations in the coolant increased, the sodium's capacity to maintain these gases in solution became saturated, leading to bubble nucleation at preferred sites within the fuel channel geometry. Gas bubble formation within sodium-cooled fuel channels created flow instability mechanisms that had been theoretically predicted but never experimentally observed under reactor conditions. The bubbles preferentially formed at heated surfaces where local sodium temperature approached the saturation point for dissolved gases, creating insulating layers that reduced heat transfer effectiveness, precisely where cooling was most critical. This reduced cooling efficiency increased local fuel temperatures, accelerating cladding corrosion and potentially triggering additional fuel failures in adjacent elements. The thermal hydraulic behavior of two-phase sodium flow differed fundamentally from the single-phase liquid conditions under which the reactor's heat removal systems had been designed and analyzed. Liquid sodium's excellent heat transfer properties depended on maintaining intimate contact between the coolant and heated surfaces, with heat removal rates that were nearly independent of flow velocity over the normal operating range. However, gas bubble formation disrupted this surface contact, creating thermal resistance layers that dramatically reduced local heat transfer coefficients, even while bulk coolant flow rates remained normal. These heat transfer degradation mechanisms created positive feedback loops where reduced cooling led to higher fuel temperatures, increased fission gas release, more extensive bubble formation, and further cooling degradation. The process was self-reinforcing once initiated, with each fuel failure making adjacent elements more susceptible to failure by increasing gas concentrations in the shared coolant stream. The reactor design's fuel element arrangement, optimized for neutron economy and normal heat removal, became a liability under these abnormal conditions by facilitating the spread of cooling degradation between neighboring fuel assemblies. The sodium coolant chemistry also played a critical role in accelerating the degradation process through mechanisms that had not been fully characterized during reactor design. Dissolved fission products, particularly iodine and cesium isotopes, reacted with magnesium cladding to form corrosion products that were less protective than the normal oxide films that provided cladding integrity under normal operating conditions. These chemical reactions were accelerated by the elevated temperatures that resulted from reduced heat transfer, creating another positive feedback mechanism where chemical and thermal degradation processes reinforced each other. The reactor's neutron flux distribution, carefully optimized for experimental objectives and fuel utilization efficiency, created preferential failure patterns that concentrated damage in high-power fuel elements while leaving other regions of the core relatively unaffected. This non-uniform damage pattern meant that bulk reactor parameters continued to appear normal even as significant portions of the core experienced serious degradation. The neutron monitoring system detected overall power levels and control rod effectiveness based on average conditions throughout the reactor, providing no indication of localized problems that affected only a fraction of total fuel elements. Control rod insertion had successfully reduced reactor power levels and fission rates, but it could not address the continued release of fission products from fuel elements that had already failed. These previously formed fission products continued to decay and release energy within damaged fuel elements, maintaining elevated temperatures and chemical reaction rates that sustained the degradation process even at reduced reactor power levels. The energy release from fission product decay represented only a small fraction of normal reactor power output, but it was concentrated in damaged fuel elements where heat removal capability had been compromised by gas bubble formation. The primary sodium circulation system transported dissolved fission products throughout the reactor cooling loop, distributing contamination to regions far from the damaged fuel elements. This transport process gradually loaded the entire primary system with radioactive materials, while gas separation at low-pressure locations in the cooling circuit created contamination reservoirs that would remain hazardous long after the reactor was shut down. The excellent mixing characteristics that made sodium an effective coolant also made it highly effective at spreading contamination throughout the primary system. As dissolved gases separated from the sodium coolant, they accumulated in expansion tank and cover gas systems that were designed to accommodate normal coolant volume changes during reactor operation. These gas handling systems were not designed to process significant quantities of radioactive gases, lacking filtration or containment capabilities that would prevent atmospheric release. The normal operation of these systems, which vented excess gases to atmosphere through stacked discharge systems, became a direct pathway for releasing fission products to the environment surrounding the facility. The atmospheric release pathway through normal ventilation systems meant that radioactive materials entered the environment through engineered systems that functioned exactly as designed, rather than through accident-induced failures that might have triggered emergency responses. Stack monitoring systems detected increased radioactivity levels in discharge gases, but these increases remained below alarm thresholds that had been established for normal operational variations, rather than accident conditions. The gradual nature of the release prevented rapid accumulation of atmospheric contamination that might have triggered automatic isolation systems. Meteorological conditions during the night of July 13 to January 14, 1959, created atmospheric dispersion patterns that transported released radioactive materials toward populated areas in Simi Valley and the San Fernando Valley. The complex terrain surrounding Santa Susana Field Laboratory created valley drainage flows that channeled atmospheric releases toward residential areas rather than dispersing them over uninhabited regions. These dispersion patterns concentrated atmospheric contamination in areas where public exposure was most likely, yet remained below detection thresholds for environmental monitoring systems that were designed to detect much higher contamination levels. The chemical form of released radioactive materials also influenced their environmental behavior and potential health effects. Iodine isotopes, which represented significant fractions of the fission products released from damaged fuel elements, readily combined with atmospheric moisture to form compounds that deposited readily on vegetation and surface water. These deposition processes created contamination patterns that would persist in the environment long after atmospheric concentrations returned to normal levels, yet occurred at concentrations too low to trigger existing environmental monitoring systems. The reactor's approach to criticality control remained effective throughout this degradation sequence, with control rods maintaining reactivity within safe margins despite the ongoing fuel failures. Neutron absorption by fission products released into the coolant actually provided additional negative reactivity that enhanced reactor shutdown margins, ensuring that reactivity control remained positive even as fuel integrity deteriorated. This maintenance of nuclear safety margins reinforced operator confidence that reactor conditions remained fundamentally safe, since criticality control had historically been the primary safety concern for experimental reactors. However, the maintenance of nuclear safety while radiological safety deteriorated created a fundamental mismatch between traditional reactor safety metrics and actual public safety status. The reactor remained subcritical and controllable according to all traditional nuclear safety criteria, while simultaneously releasing radioactive materials to the environment at rates that exceeded all previous experience with reactor accidents. This contradiction between nuclear safety and radiological safety would not be recognized until much later analysis revealed the extent of environmental contamination that had occurred. By dawn on July 14th, the physical situation within the reactor core had stabilized at a new equilibrium, where ongoing fuel failures balanced the reduced driving forces created by lower reactor power levels. Additional fuel elements continued to fail at a steady rate, as accumulated gas bubbles gradually compromised cooling in previously undamaged regions, but the rate of new failures had decreased as reactor power reduction lowered thermal driving forces. This quasi-steady degradation created conditions where reactor parameters appeared stable while environmental releases continued at elevated but constant rates. The reactor had achieved a stable configuration that appeared satisfactory from an operational perspective while remaining fundamentally unacceptable from a radiological protection standpoint. Power levels were controlled, cooling systems were circulating normally, temperatures were acceptable, and control systems were responsive. Yet the reactor was systematically releasing radioactive materials to the environment through normal operational pathways, while providing no indication to operators that public safety was being compromised. This divergence between operational success and radiological safety would define the remainder of the incident sequence. The reactor shutdown sequence initiated at 6:45 PST on July 14, 1959, proceeded according to established procedures that had been successfully demonstrated dozens of times during the sodium reactor experiment's operational history. Control rods inserted fully within 30 seconds, neutron flux decreased to subcritical levels within 2 minutes, and primary sodium circulation continued at reduced flow rates to provide decay heat removal. From the operator's perspective, the shutdown represented a routine precautionary measure in response to minor operational irregularities rather than an emergency response to serious reactor damage. However, the shutdown process that successfully terminated nuclear fission could not address the ongoing release of fission products from fuel elements that had already sustained cladding damage. Radioactive isotopes trapped within failed fuel elements continued to decay at rates determined by their nuclear half-lives rather than reactor operating status, releasing decay energy that maintained elevated temperatures in damaged fuel regions. This decay heat, representing approximately 3% of normal reactor power immediately after shutdown, was more than sufficient to sustain the chemical and thermal processes that had initiated fuel degradation during reactor operation. The decay heat removal system for the sodium reactor experiment relied on continued sodium circulation through natural convection and reduced capacity pumping systems that were adequate for removing heat from intact fuel elements under normal shutdown conditions. However, the gas bubbles that had accumulated in damaged fuel channels during reactor operation continued to interfere with heat removal effectiveness, even at reduced power levels. The natural convection flows that provided backup cooling were particularly susceptible to disruption by gas accumulation, since these flows depended on small density differences that could be overwhelmed by gas bubble effects. Temperature monitoring during the initial hours after shutdown indicated apparently successful decay heat removal, with bulk coolant temperatures stabilizing at values consistent with reduced reactor power output. However, these bulk temperature measurements continued to mask localized hotspots where gas bubbles prevented effective heat removal from damaged fuel elements. The temperature distribution within individual fuel elements became increasingly non-uniform as decay heat production continued, while local cooling capability remained compromised by accumulated gases. Operations personnel faced a fundamental challenge in assessing actual reactor conditions during the post-shutdown period, since their instrumentation systems provided no direct indication of fuel element integrity or gas accumulation effects. Normal shutdown procedures assumed that temperature and flow measurements provided adequate indication of successful decay heat removal, an assumption that remained valid for intact fuel elements but became progressively less reliable as gas effects accumulated. Operators observed apparently normal cooling system performance while actual heat removal from damaged fuel elements continued to deteriorate. The primary sodium system's chemical behavior during shutdown created additional complications that had not been anticipated in normal shutdown procedures. Fission products dissolved in the sodium coolant began to plate out on cooler surfaces throughout the primary system as circulation rates decreased and temperature gradients changed. This deposition process created contamination patterns in pumps, heat exchangers, and piping systems that would remain radioactive long after the reactor was permanently shut down, yet occurred through normal mass transfer processes that provided no immediate indication to operations personnel. The cover gas system that managed pressure equilibrium in sodium expansion tanks continued to vent radioactive gases to atmosphere through normal operational pathways, since shutdown procedures did not automatically isolate these systems during routine shutdowns. The venting process that had provided acceptable contamination control during normal operations continued to release fission products at rates that were elevated but not dramatically different from previous operational experience. This gradual release pattern prevented triggering automatic isolation systems while maintaining steady atmospheric contamination that exceeded normal background levels. Emergency response procedures activated during the shutdown focused on verifying reactor subcriticality and ensuring adequate decay heat removal, rather than assessing potential off-site radiological consequences. Emergency response teams conducted systematic checks of control rod position, neutron monitoring systems, and cooling system operation according to established protocols that were appropriate for normal reactor shutdown sequences. These procedures were designed to verify that reactor conditions remained safe for facility personnel, but did not include systematic assessment of environmental contamination levels or potential public exposure. The facility's radiation protection organization began implementing increased monitoring procedures during the hours following shutdown, installing additional contamination detection equipment, and increasing the frequency of routine surveys. However, these monitoring enhancements focused on detecting contamination levels that might affect facility workers rather than assessing environmental contamination patterns that might indicate off-site releases. The radiation protection procedures assumed that significant environmental releases would be associated with dramatic reactor accidents that would provide clear indication through multiple instrumentation channels. Health physics personnel detected elevated contamination levels in various facility areas during the post-shutdown period. But these increases were attributed to normal, operational variations associated with reactor shutdown, rather than indication of serious fuel damage. The contamination patterns observed were consistent with previous experience during planned shutdown operations, when stirring of sodium systems typically redistributed accumulated contamination and temporarily elevated facility radiation levels. This interpretation was reasonable based on available information, but failed to recognize that the contamination sources had fundamentally changed from normal operational accumulation to active fuel element failure. Air sampling systems throughout the facility detected increased concentrations of airborne radioactivity during the post-shutdown period, but these increases remained below action levels that had been established for emergency response activation. The air sampling network was designed to detect dramatic increases in airborne contamination that might indicate serious reactor accidents, with alarm thresholds set accordingly. The gradual increases actually observed suggested unusual but manageable operational conditions rather than emergency situations requiring immediate response. The decision-making process for determining appropriate response actions reflected the fundamental ambiguity between observed conditions and actual radiological status that characterized the entire incident sequence. All available information suggested successful reactor shutdown with minor operational complications that could be managed through established procedures. Radiation detection systems showed elevated but manageable contamination levels. Reactor parameters indicated successful shutdown, and cooling systems appeared to be functioning adequately for decay heat removal. However, this apparently successful shutdown masked ongoing processes that were creating long-term radiological consequences far beyond facility boundaries. Atmospheric releases continued through normal ventilation pathways. Environmental contamination accumulated through deposition processes, and contamination within the facility spread through normal operational activities. The reactor had achieved nuclear safety through successful shutdown, while radiological safety continued to deteriorate through mechanisms that remained largely invisible to facility monitoring systems. Investigation efforts during the immediate post-shutdown period focused on identifying the cause of operational irregularities that had prompted the precautionary shutdown rather than assessing the extent of fuel damage or environmental consequences. Engineering teams began systematic evaluation of reactor systems to determine why power level transients had occurred, examining control system behavior, instrumentation performance, and cooling system operation. These investigations followed established procedures for determining causes of operational problems, but were not designed to assess fuel integrity or contamination levels. The reactor remained in shutdown condition, with cooling systems operating and monitoring systems indicating stable conditions throughout the remainder of July 14, 1959. Operations personnel maintained normal post-shutdown surveillance, while engineering teams continued investigating the operational irregularities that had prompted shutdown. From all available indications, the reactor had been successfully shut down and stabilized following minor operational problems that appeared to have been resolved through appropriate procedural responses. Yet the physical reality within the reactor core and primary system continued to evolve in ways that would create lasting environmental and public health consequences. Damaged fuel elements continued releasing fission products into sodium coolant that transported contamination throughout the primary system. Gas accumulation effects persisted, maintaining localized hotspots where decay heat could not be effectively removed. Atmospheric releases continued at elevated rates through normal operational pathways that provided no indication that environmental contamination was accumulating at unprecedented levels. The apparent success of shutdown and stabilization procedures created institutional confidence that the reactor incident had been successfully managed without significant consequences. This confidence was supported by all available instrumentation and monitoring data, which indicated normal post-shutdown conditions with manageable radiation levels throughout the facility. The decision to classify the incident as a minor operational problem rather than a significant accident reflected reasonable interpretation of available information, yet this classification would prevent appropriate assessment of actual environmental and public health impacts for decades to follow. The comprehensive post-incident investigation that began in August 1959 revealed the full extent of fuel element damage through physical examination techniques that had been impossible to implement during reactor operation. Removal of damaged fuel assemblies from the reactor core showed that 13 of the 43 fuel elements had experienced varying degrees of cladding failure, with the most severely damaged elements showing complete loss of cladding integrity over significant portions of their length. These physical findings confirmed that the reactor had sustained core damage far exceeding what had been indicated by operational instrumentation during the incident sequence. Metallurgical analysis of failed fuel element cladding revealed failure mechanisms that were consistent with thermal stress combined, with accelerated corrosion in the presence of dissolved fission products. The magnesium cladding had experienced intergranular cracking that propagated along grain boundaries weakened by chemical attack from iodine and cesium isotopes released from the uranium-molybdenum fuel alloy. These failure mechanisms had been theoretically predicted, but never experimentally observed under actual reactor operating conditions, providing validation of materials science models while demonstrating their practical consequences for reactor safety. Examination of fuel element internal structures showed that the uranium-molybdenum alloy had undergone phase changes and microstructural rearrangement, consistent with operation at temperatures significantly above design specifications. These metallurgical changes indicated that fuel temperatures had reached levels where thermal expansion and chemical reactivity overwhelmed the mechanical integrity of the fuel cladding system. The physical evidence demonstrated that normal reactor instrumentation had been inadequate to detect these extreme local conditions while they were developing. Chemical analysis of sodium coolant samples revealed fission product concentrations that were orders of magnitude higher than had been detected during reactor operation. The analytical techniques available in 1959 were not sufficiently sensitive to detect these contamination levels in real time, explaining why coolant monitoring had not provided indication of fuel element failures during reactor operation. Post-incident analysis using more sophisticated techniques revealed that massive quantities of fission products had been released into the primary coolant system without triggering any automatic detection systems. Environmental sampling programs implemented months after the incident detected radioactive contamination in soil, vegetation, and surface water at significant distances from the reactor facility. Iodine 131 concentrations in milk samples from local dairy farms indicated that atmospheric releases during the incident had created exposure pathways to the local food supply that had been completely unrecognized during the incident sequence. These environmental findings demonstrated that significant public exposure had occurred without triggering any emergency response or public notification procedures. Atmospheric dispersion modeling reconstructed from meteorological records showed that radioactive materials released during the incident had been transported directly over populated areas in Simi Valley during the early morning hours of July 14, 1959. The combination of terrain-induced drainage flows and stable atmospheric conditions had concentrated contamination in residential areas where thousands of people were potentially exposed to elevated radiation levels. This exposure had occurred without any public awareness or protective actions, since no environmental monitoring systems had detected the releases in real time. Reconstruction of the release quantities based on environmental sampling data indicated that the Santa Susana Field Laboratory incident had released substantially more radioactive material to the environment than would be released 15 years later during the 3 Mile Island accident. The total release included significant quantities of iodine 131, cesium 137, and other fission products that created long-term environmental contamination patterns extending well beyond facility boundaries. However, the absence of containment structures at Santa Susana meant that these releases occurred directly to atmosphere rather than being filtered or delayed by engineered safety systems. The institutional response to these forensic findings reflected military nuclear program priorities that emphasized information control over public health protection. Investigation results were classified at high security levels that prevented independent scientific review or public disclosure of environmental contamination findings. This classification system functioned effectively to protect nuclear program security interests, but eliminated the possibility of systematic public health monitoring or medical surveillance that might have identified health effects in exposed populations. Health effects analysis was further complicated by the absence of baseline health data for populations surrounding the facility and the lack of systematic exposure assessment during the incident. The delayed recognition of significant environmental releases meant that critical exposure pathway information was lost, preventing accurate reconstruction of individual doses or population exposures. Epidemiological studies conducted decades later would be limited by these fundamental data gaps, making it impossible to definitively establish causal relationships between incident exposures and subsequent health effects. The regulatory response to the Santa Susana incident led to fundamental changes in nuclear reactor safety requirements that addressed the specific failure mechanisms that had been identified. Future experimental reactor designs were required to include containment structures regardless of coolant type, eliminating the assumption that liquid metal reactors were inherently safer than water-cooled designs. Instrumentation requirements were expanded to include direct monitoring of fuel element integrity and fission product release, rather than relying solely on bulk coolant property measurements. Reactor operator training programs were restructured to emphasize recognition of fuel failure symptoms and appropriate emergency responses rather than focusing primarily on maintaining reactor control during transients. The incident demonstrated that technical competence in reactor operation was insufficient for protecting public safety when reactor conditions exceeded design basis assumptions. Emergency operating procedures were rewritten to include shutdown criteria based on fuel integrity indicators rather than relying exclusively on traditional nuclear safety parameters. Environmental monitoring requirements for reactor facilities were substantially enhanced to include real-time detection of atmospheric releases and comprehensive environmental surveillance programs. The Santa Susana incident had demonstrated that significant environmental contamination could occur without detection by monitoring systems designed for normal operational conditions. Future reactor licensing required monitoring systems capable of detecting accident-level releases and triggering appropriate emergency responses. The incident also revealed fundamental inadequacies in the institutional framework for managing experimental nuclear facilities near populated areas. The regulatory structure that had permitted uncontained reactor operations in proximity to residential development was recognized as inappropriate for protecting public safety. Future experimental reactor programs were subject to enhanced regulatory oversight that treated experimental uncertainty as a safety concern rather than an acceptable operational characteristic. Emergency response planning requirements were expanded to include off-site consequences and public protective actions rather than focusing exclusively on facility protection and information security. The Santa Susana incident had demonstrated that reactor accidents could create significant public exposure without any indication through facility-based monitoring systems. Emergency planning was restructured to assume that serious reactor accidents would require public notification and protective actions regardless of facility monitoring system indications. The long-term environmental cleanup of the Santa Susana site revealed the extent of contamination that had accumulated from decades of experimental nuclear operations, including the 1959 incident and subsequent operational releases. Soil contamination extended far beyond facility boundaries, requiring extensive remediation efforts that continued for decades after reactor operations ceased. The cleanup process provided additional validation of the environmental release estimates that had been reconstructed from the 1959 incident, confirming that major environmental contamination had occurred without contemporary recognition. The Santa Susana Field Laboratory incident demonstrated that reactor safety could not be assured through technical competence and regulatory compliance alone, when fundamental design assumptions proved invalid under abnormal conditions. The highly skilled personnel who operated the reactor followed established procedures and maintained technical control throughout the incident sequence, yet these same factors contributed to massive environmental releases that endangered public health. The incident revealed that reactor safety required systematic consideration of failure mechanisms that exceeded design basis assumptions and institutional frameworks that prioritized public protection over operational objectives. The most significant lesson from the incident was the recognition that experimental reactor programs carried inherent uncertainties that could not be managed through normal operational procedures or regulatory oversight designed for commercial nuclear facilities. The institutional framework that had treated experimental reactors as extensions of established nuclear technology proved inadequate when experimental conditions created failure mechanisms that were outside previous experience. Future experimental programs required fundamentally different approaches to safety analysis, operational procedures, and emergency response that acknowledged experimental uncertainty as a primary safety consideration rather than a manageable operational characteristic.